Welcome to this channel. Today we will extend our discussion on motion in one dimension to instantaneous velocity and acceleration. Now we shall talk about both the average and instantaneous acceleration today. Let's begin with velocity in general. Well, it is a vector, and the SI unit to measure velocity is meter per second. Now, loosely speaking, velocity measures how fast something is moving in a particular direction. The direction of this velocity vector follows the direction of the motion. So if this is the direction of motion, then the direction of the velocity is represented by this red arrow. So direction of this velocity vector is the same as the direction of motion. So if motion of an object is along, let's say, I hat, then its velocity is also along I hat. An important thing to note about velocity in one dimension is that as the object travels along this line, let's say along the x-axis, and then it comes to a certain point, and then it decides to change direction, let's say point x naught. So at the point where it reverses its direction, the velocity becomes 0. So whenever an object changes direction, the velocity at the point where it changes its direction becomes 0. Now let's look at instantaneous velocity. Instantaneous velocity of a moving object is the velocity at a particular instant, or velocity at a particular time t. So the way we represent or write this instantaneous velocity is like this, as a function of time. The mathematical definition of instantaneous velocity is as follows. So instantaneous velocity is given by the time derivative of the changing position vector. So this is the changing position vector. As the object moves, the position vector changes. So it's a function of time as well. So the rate of change of this position vector is the instantaneous velocity. So for an object that's moving along the positive x-axis as shown in this diagram, the position vector of this object is rt. And if the x-coordinate at a particular instant is xt, then the rt, the position vector, can be written as xt I hat. And the expression for the instantaneous velocity for this object is given by that expression in that green box, d dt xt I hat. Likewise, if an object is moving vertically along the y-axis as shown in the diagram, and yt is the y-coordinate of this object at any time t, then its position vector is written in the following form. It's ytj hat. And the instantaneous velocity for this vertical motion, it's given by this expression. Note the j hat there. Let's look at the following example on instantaneous velocity. So you have a particle moving along the x-axis, and the coordinate is given by that. It's changing according to that equation. And you are interested in determining the velocity of the particle at t equals to 3. So instantaneous velocity at t equals to 3 seconds. And also in what direction of the particle moving at that time. So we will use the definition for the instantaneous velocity to compute the velocity of the particle at t equals to 3 seconds. So we end up differentiating 12t squared after substituting 12t squared for the xt. And of course, the result of this differentiation is 24t I hat. So at t equals to 3, it simply becomes 24 times 3 I hat, which is 72 I hat meter per second. So this is the instantaneous velocity of the object at t equals to 3 seconds. And the direction of this particle at that time is given by this I hat. So we say it's moving along the positive x direction. Now let's look at another example The particle's position is given by this expression. X is measured in meters, t is in seconds. Calculate its velocity at t equals to 1 second. So that is the instantaneous velocity at t equals to 1. What is the speed just then? That means that's the instantaneous speed at t equals to 1. And find the time when the velocity is 0. By using the definition of instantaneous velocity, we arrive at the following. So the derivative of 4 is 0. The derivative of minus 12t is minus 12. Derivative of 3t squared is 6t. So you end up with the following expression for the instantaneous velocity. So minus 12 plus 6t I hat, which then yields the answer minus 6 I hat meter per second for the velocity at t equals to 1. Now what about the speed at that time? So the speed is the magnitude, the instantaneous speed is what we are calculating here, is the magnitude of the instantaneous velocity. So in this case, it is quite simply 6 meter per second. The final part asks you to find the time when the velocity is 0. Now since the velocity, the instantaneous velocity, was found to be minus 12 plus 60 I hat, so we simply have to solve when this expression goes to 0. So immediately we'll see that by setting minus 12 plus 60 to 0, it yields t equals to 2 seconds. So at t equals to 2 seconds, the velocity of this object is 0. A careful inspection reveals that at t equals to 2 seconds, the object is actually changing its direction. This can be seen from the following. At t less than 2 seconds, the instantaneous velocity is along the direction of minus I hat. At t equals to 2 seconds, the instantaneous velocity vanishes. And at t equals to greater than 2 seconds, the instantaneous velocity is in the direction of positive I hat. So these are the indications that the object is actually changing its direction at t equals to 2 seconds. We next look at acceleration. It is a vector, and the SI unit to quantify acceleration is meter per second squared. So it measures how much velocity changes over a given time interval, or you can also look at it as a rate of change of velocity. What that means is if you have an object with an acceleration of, let's say, 1 meter per second squared, and at some point in time its velocity is 2 meter per second I hat, which means the object is moving to the right. Now 1 second later, let's say the object is now here, the speed now will be 3 meter per second I hat because of the acceleration being 1 meter per second squared, which means the speed is increasing at a rate of 1 meter per second every second. And again, up to another second later, the speed now would have increased by another 1 meter per second. So now it is 4 meter per second I hat, and so on and so forth. Now let's try to understand the direction of acceleration. If an object is speeding up, the acceleration is positive, meaning the acceleration is also going in a rightward direction, along I hat direction. Now, if the object is slowing down, we say it is decelerating, or the acceleration being negative. Now, if the motion is still to the right, or the velocity is to the right, the acceleration now is heading backwards because now the object is decelerating. So the first case, the positive acceleration case, it's called acceleration, and the negative acceleration case, it's called the deceleration, where the object is actually slowing down. Let's look at two different versions of acceleration. The first one is the average acceleration. The definition of average acceleration is it represents or it measures the change in velocity over a time interval. So if you have an object moving to the right as shown, when the object was at the initial point, the velocity was vi, and when the object gets to the final point, the velocity is v sub f. So the change in the velocity over these 2 points is vf minus vi. And let's say it takes delta t seconds for the change to occur. And the average velocity is given by this following expression, vf minus vi over delta t. Note that if the final velocity is greater than the initial velocity, the average acceleration is positive. The object is speeding up. If the final velocity is less than the initial velocity, the average acceleration is negative or the object is slowing down. Let's do the following example. At a certain time, an object's velocity was 18 meter per second I hat. After 3 seconds, the velocity is minus 30 meter per second I hat. Calculates its average acceleration over this time interval. So the average acceleration expression is given by that as shown. So we know that the final velocity is minus 30 I hat. Initial velocity is 18 I hat. Time interval is 3 seconds, and that's going to be minus 48 I hat over 3. So the final answer is minus 16 I hat meter per second squared. Now let's look at the instantaneous acceleration. It is an acceleration at a particular time t, and it is not measured over a time interval. The mathematical definition for instantaneous acceleration is as given, so it represents the rate of change of velocity. And note that since instantaneous velocity can be written as time derivative of position vector, then instantaneous acceleration can be written as the second time derivative of the position vector. In this example, a particle's position is given, the y-coordinate of it, and you want to calculate the instantaneous velocity at t equals to 1 second, the average acceleration between t equals to 0 and 2 seconds, and instantaneous acceleration at t equals to 2 seconds. The instantaneous velocity expression is given as below, time derivative of the y-coordinate, and ended up taking the derivative of 2 sine pi t over 4. So from calculus, we obtain this line, derivative of sine is cosine. So upon substituting t equals to 1 in here, you end up getting that, and calculating the numerical value gives you 1.1 j hat meter per second for the instantaneous velocity. The average acceleration can be determined from the definition as shown. So substituting the expression for the velocity, the instantaneous velocity at 2 different times, we end up getting this step, and finally you get the following. So 0 minus 1 over 2 j hat, which is minus 0.79 j hat meter per second squared. Next, the instantaneous velocity, which is given by the shown expression here. And using calculus, one obtains the following. Now substituting t equals to 2, one gets the final answer as minus 1.2 j hat meter per second squared. In summary, we see that one could go from position vector to instantaneous velocity to instantaneous acceleration by taking successive time derivatives as shown in this page. Next time we shall look at the reverse order through integration. We shall also discuss various graphical analysis associated with those variables. I hope you found the content of today's video useful. Thanks for watching.